super happy to be here to talk about using a thin client approach to build command line interfaces that interact with web services. My name is Jeremy Evans. I'm a Ruby committer. I'm also the maintainer of Sequel, Roda, Rodoth, and many other gems. I'm a principal software engineer at Ubicloud. We are building an open source alternative to Amazon Web Services. Now, since shortly after Ubicloud was founded in 2023, it supported provisioning resources such as virtual machines using both a browser interface and an API. And earlier this year, we decided to add a command line interface that used that API so users could do things like add and remove virtual machines from the command line without any custom programming. I was assigned responsibility for implementing this CLI. And while I've written numerous command line programs in my career, I had not yet written one that was nearly as large as the intended scope. Now, one way to create such a CLI is by using what I'll call the traditional approach. And here's what the traditional approach looks like. In this diagram, client is the command line program that's running on the user's machine, and target is the API endpoint that the client needs to send the request to. And when you run the client, it processes the array of arguments, determines what type of request is being made, and determines what target endpoint needs to be contacted. After determining the target endpoint to contact, the client prepares the body of the request, assuming the request needs a body, and then it sends the request to the target endpoint. The target endpoint handles the request and performs the appropriate action, and then returns a response in JSON format. The client parses that JSON response and formats the text to display to the user, and that's what the traditional approach looks like when building a command line interface to interact with web services. I think the biggest advantage of the traditional approach is that it's simple. There's only two parts, the client and the target endpoint. And all else being equal, simpler solutions are better than more complex solutions. However, all else is not equal in this case, as there are some significant disadvantages to the traditional approach. Now, the main disadvantage when using the traditional approach is if you add a new API feature, such as a new target endpoint, the client running on the user's machine cannot use it. The user would need to update their client to a version that supports the new API feature. And forcing users to update their clients to use new API features results in increased friction. One approach to addressing this disadvantage is to use an auto-updating program. However, this adds complexity and introduces security issues to users, and many users do not want a command line program like this to auto-update. With the traditional approach, you lose the primary advantage of web-based software development over traditional desktop software development, which is as soon as you put a new feature into production, it is immediately usable by users of the website. Now imagine, if every time that you added a feature to your website, your users had to update their browsers in order to use it. I mean, preposterous, right? But that's basically what the traditional CLI approach requires. Now, the other less important disadvantage is in error handling. With the traditional approach, errors that occur in parsing the command line arguments, building the request body, and parsing the response from the target endpoint all occur on the user's machine. You have to hope that the users report the errors. I mean, you can't have errors auto-reported, but many users are against that type of telemetry, and there can always be bugs in the auto-reporter that prevent notifications about the errors. Now that I've discussed the traditional approach, let's examine the thin client approach and see how it compares. And here's what the thin client approach looks like. Now, the client in this diagram is still the command line program, and the target is still the API endpoint. The thin client approach introduces the idea of a gateway endpoint. And most of the logic that is in the client program in the traditional approach is performed by the gateway endpoint in the thin client approach. With the thin client approach, the client doesn't even parse the array of arguments received. Instead, it formats them as a JSON array and sends a post request to the gateway endpoint with that JSON in the request body. Now, the gateway endpoint is a single HTTP route that accepts a JSON array of strings, which are the command line arguments passed to the client. The gateway endpoint parses this JSON array and determines the target endpoint to contact. The gateway endpoint formats a request body if needed and sends the request to the target endpoint. Now, there's no requirement that the gateway endpoint be running in the same process as the target endpoint, though they are in Ubicloud's case. In Ubicloud's implementation, instead of sending an HTTP request to the target endpoint, the gateway endpoint calls the target endpoint rack application directly with a rack environment hash. But you could easily implement a gateway endpoint that ran on a different machine and contacted the target endpoints using HTTP requests. Now, the target endpoint does the same processing it did previously. There's no difference in how the target endpoint handles requests. There's also no difference in the response provided by the target endpoint. No changes to the target endpoint are needed when introducing the thin client approach. The gateway endpoint is operating as a normal client from the perspective of the target endpoint. Now, instead of the client parsing the JSON response and formatting it, the gateway endpoint parses the JSON response, and it formats it as a plain text response that's suitable for the client to print directly. The gateway then sends this plain text response to the client, and all the client needs to do is print that pre-formatted text to the standard output, or if the HTTP response status indicates an error, to the standard error. Because the client does so little when using the thin client approach, it can be very small. It only needs to know how to submit an HTTPS request, how to format JSON, and how to print to the standard output or standard error. It doesn't need to know how to parse JSON or how to format the text being printed. It doesn't need to have any logic at all specific to the API being contacted. Just prints the response body to the terminal. A minimal thin client in Ruby could probably be under 50 lines and probably under a couple hundred lines in a lower level language. Almost all of the logic that was in the client in the traditional approach is moved to the gateway endpoint in the thin client approach. And that's what gives the thin client approach its advantages. The main advantage is instant deployment. When adding a new target endpoint, you can update the gateway endpoint to support CLI access to the new target endpoint at the same time. Users can use new CLI features without updating their client program, and this brings the advantages of web deployment to command line interfaces. Most non-network errors that occur in the client program in the traditional approach now instead occur on the gateway endpoint in the thin client approach. And that's better because the gateway endpoint is running on a server you control. And any exceptions raised by the gateway endpoint, you can process in the same manner that you would handle for any other errors that occur during server-side processing. As the client's small, it's simple to port to other languages. And that's useful because in general, you want to provide your users dependency-free static executables. And not all languages make it easy to do that. If all of the logic has to be in the client, you have a tough choice between wanting to use a friendly language for that logic versus needing to use a language that can build dependency-free static executables. Because all of the logic moves from the client to the gateway endpoint, you can implement that logic in the same language that you use to implement the target endpoints, which for Ubicloud, and I'm assuming for most of you, is Ruby. When you consider command line argument parsing, determining the target endpoints, handling responses from the target endpoints, and formatting those responses into plain text, I think it's vastly more preferable to use Ruby for those things than it would be to use a lower level language that makes it easy to build dependency-free static executables. A small advantage of the thin client approach is less latency if a command requires accessing multiple target endpoints. Now, with the traditional approach, if the client needs to send multiple requests to separate target endpoints, where the output of the first target endpoint is needed to determine the next target endpoint, each of those requests could have significant latency. With the thin client approach, the client only needs to make a single request to the gateway endpoint, and the gateway endpoint handles the internal request to the target endpoint. The gateway endpoint has much less latency to the target endpoint than the client does, so in general, any requests that require multiple target endpoints have lower overall latency with the thin client approach. The flip side of this is because there is no logic on the client, all command executions require a request to the gateway endpoint, and that includes commands for help or to get the program version. In the traditional approach, the client can provide that information without submitting a request, but with the thin client approach, it requires a request. Additionally, if a command requires confirmation, the traditional approach can ask for confirmation up front before submitting the request, while the thin client approach requires multiple requests, since the server must respond to the original request asking for confirmation. If the client needs to execute external programs, you have other issues to consider. For example, Ubicloud's client supports executing SSH, SFTP, and SCP to connect to created virtual machines. It also supports executing PSQL, pgdump, and pgdumpall to connect to created PostgreSQL databases. When executing external programs based on a server response, you cannot fully trust the server. If the server tells the client to delete all files in the user's home directory, you don't want the client to do that. Safe external program execution requires deviating from a pure thin client approach and implementing API-specific logic in the client. And the majority of logic in Ubicloud's command line program deals with checking the external program and the arguments that the server is asking the client to execute. Now, in order to execute an external program, the Ubicloud client requires the program name to exactly match one of these 6. And it also requires the program name requested by the server be one of the command line arguments that was passed to the client. So there's a clear indication that the user running the client is expecting external program execution. Additionally, at most one argument to the external program can be new. All other arguments to the executed program must already be included in the command line arguments that were passed to the client. The arguments to the external program must include -- to separate command line options from command line arguments, except for pgdumpall, which doesn't support this. And the new argument must appear after -- and this allows the server to provide a new argument to the executed program, but not a new option to the executed program. pgdumpall doesn't support this, so for pgdumpall, the new argument must start with -d. And those restrictions are sufficient to allow Ubicloud's client to safely execute all 6 programs. And these restrictions are hard-coded into the client. So if we want to support additional external programs in the future, users would have to update their clients. And that doesn't negate the main advantage of the thin client approach. But it's expected that adding new external programs will be infrequent, and executing programs on users' machines without these checks is too dangerous. So this seems like a reasonable compromise. Now, using the thin client approach requires you to consider how to configure the client. Ubicloud's client requires an authentication token to work at all. For testing or to use a custom server, you would want to configure the gateway endpoint to contact. With a pure thin client approach, you cannot configure the program using a command line argument because the client doesn't parse the command line arguments. That's possible to support configuration via a configuration file. However, you would have to hard code the configuration file location. You could not provide a configuration file location using a command line option. This was considered too limiting for Ubicloud, and as the only required configuration option is an authentication token, we assume that many enterprise security teams would not want it stored in a file. So we chose to handle all configuration using environment variables. And this allows users to choose their own approach based on their risk preference. Users with a large risk appetite may want to set the environment variables in their shell for ease of use. My risk appetite isn't that large, so I use a wrapper script that sets the environment variables and then executes the program. And a wrapper script isn't necessarily better than a configuration file, but the important thing is the user has control over how to provide the configuration. After deciding to use the thin client approach, I started building a prototype of the client program. Unsurprisingly, I built the prototype in Ruby. We still maintain the Ruby version in our repository. It uses only NetHTTP and JSON libraries, no external gems, and it runs correctly on Ruby 2.4 and later. And while this doesn't have any dependencies other than Ruby, Ruby itself is a dependency. We want to provide the user a dependency-free static executable. And while Ruby is great at a lot of things, building dependency-free static executables is not one of those. Now, that may be changing into the future due to Tobacco, which is a recently developed packaging tool. However, packaging Ruby applications with Tobacco builds relatively large executables, and using Tobacco requires some other restrictions that make it suboptimal for our usage. Now, while the standard Ruby implementation is not good at building dependency-free static executables, mRuby allows you to compile your Ruby code to C and then build a dependency-free static executable using a C compiler. And this static executable will embed the mRuby virtual machine to run the Ruby code. But from a user perspective, it's similar to other static executables, and it does not require any dependencies installed on the user's machine. Unfortunately, I quickly found that while mRuby is for the most part syntax compatible with Ruby, it is not library compatible with Ruby. There's no require. and the net HTTP and JSON libraries are not standard libraries in mruby. Now for JSON, I found an mruby JSON library, which worked fine, and it was API compatible for my usage. Replacing net HTTP was slightly more challenging, but after trying a couple mruby libraries, I did get mruby curl to work. It's not API compatible with net HTTP, so it required some code changes, but they were not extensive. Now when building an executable that embeds mruby, the recommended approach is to run mrbc with the -B option. It compiles your Ruby code to mruby bytecode that is stored in a C array. Then you run a small C program that sets up the mruby virtual machine and then executes the mruby bytecode in that C array, and then use a C compiler to compile that C program. And as long as you tell the C compiler to build a static executable, you should end up with a dependency-free static executable. Now, that didn't work on my system because I didn't have the static libraries for libcurl or libssl installed. It would likely have worked if I did, but I realized something before trying that. We didn't just want a dependency static executable for the operating system and platform that I was running. We wanted dependency-free static executables for all common operating systems and platforms. What we really wanted was cross-compiled dependency-free static executables. Because when you're building 7 separate executables to provide to users, it's much simpler to cross-compile them from a single machine than it is to have 7 separate build machines. And doing that with mruby curl would require building cross-compilation environments for libcurl and libssl. And not having significant experience in cross-compiling C code, and honestly, not too eager to get experience with that, I decided to try another language that supports cross-compilation as a built-in feature. I chose Zig. I had no previous Zig experience, but I had heard good things about the language, and Zig is known for good cross-compilation support. I decided to port the prototype Ruby program to Zig. It's only about 100 lines, shouldn't be that difficult. I decided to enlist the help of an AI service for the initial porting, and this definitely saved time. What it did not result in is working code. The generated Zig code had the typical issues when using older AI, called functions that weren't defined, defined functions that weren't called. Now Zig's syntax is not forgiving. It took 2 solid hours of work before it would even compile successfully. When I finally got it to compile successfully, I felt like Sisyphus, finally getting this boulder to the top of the hill. And this is an especially appropriate metaphor, because when I ran the program, seg faulted. And I determined this wasn't a problem with my Zig installation, but in the AI-generated code or my changes, because I could compile simple Zig programs and run them fine. However, because I didn't have any Zig experience, and I didn't start from a working simple implementation and gradually add complexity, I wasn't well qualified to debug this issue. So I decided to try another language. I picked Go. Go is a higher level language than Zig, and while it had been over a decade since I last used it, I still had some familiarity with it. Again, started by porting the Ruby prototype to Go using the same AI service. And I had about the same results that it did with Zig. Defined functions that weren't called functions that weren't defined, didn't require necessary libraries, required unnecessary ones. However, it was a decent start. It only took about an hour to get all of the syntax errors to fix and get it to compile correctly, and then the moment of truth came. I ran the program, and it didn't segfault. Now, it didn't work correctly. It printed an error. But after another hour of debugging, it passed the test suite that I had written for the prototype. Additionally, the test suite ran 30 times faster with the Go version than with the prototype Ruby version, mostly due to avoiding Ruby startup overhead. To see how far AI has come this year, I tried using Claude code to do the same Ruby to Go conversion earlier this month. And this is the prompt I gave it. Convert the bin ubi Ruby program to a bin ubi.go Go program while keeping identical behavior as much as possible. The generated Go code compiled correctly after removing a single unused variable, and the generated executable passed over 2/3 of the tests. Quite the improvement from the results from earlier this year. Now, cross-compiling with Go is very easy. You just need to pass a couple of environment variables, goAus and goarch when compiling, and within another 15 minutes, I had cross-compiled, dependency-free static executables for all common operating systems and platforms. We released the initial version of these executables in March, and so far, we've only had to update them once. We've made many improvements and added many new API features since March, but none of those have required a new client. If you use the original client, it still works. In general, we can add new CLI features at any time and have users benefit from them immediately after deployment. Because the executables are statically linked, security issues in one of the embedded libraries may require users download a new executable to be protected. However, because the client program is so small and only uses the Go standard library, security issues should hopefully be infrequent. Now, in order to handle a CLI request, the first step is parsing command line arguments on the gateway endpoint to determine what request is being made and what target endpoint should be contacted. Here are examples of the types of commands that we want to support. We want to support top-level commands, mainly for easy help output. Each command needs to be able to support options and either a fixed or variable number of arguments. We want to support subcommands and have the same ability for subcommands that we have for commands. We also want an approach where subcommands can follow command arguments. And this allows the user to think about the object being modified and then the action to take on that object, which in many cases is more natural than thinking about what action to take and then thinking about what object should I perform this on. I consider this a more object-oriented command line style. When using this style, we also want to be able to provide options between command arguments and subcommands so that subcommands can share option parsing. There are numerous Ruby libraries dedicated to parsing command line options, and I did a review of the most popular ones to determine whether they would meet our needs. So two popular libraries, Commander and GLI, appear to support commands but not subcommands. Dry CLI supports both commands and subcommands. However, it didn't appear to support options between commands and subcommands or subcommands after command arguments. Thor is the most popular argument processor for Ruby, and it supports both commands and subcommands, and it supports option parsing at every level. However, it didn't appear to support subcommands after command line arguments. So I did what any self-respecting programmer does when they can't find a library to do what they need, and I wrote my own argument parsing library. Now, parsing command line arguments is in many ways similar to parsing paths in web requests. And I have a lot of experience doing that in Roda. I originally played around with writing this argument parsing library as a Roda plugin, and while it worked, it was suboptimal, mostly because it's expensive to build the option parsers per request. And that's a problem you don't have when you're parsing paths. I ultimately ended up building a Rodish library to handle the argument parsing. And this allows for the separation of the static and dynamic parts of parsing command line arguments. So the static parts would be like the help text and the option parser. The dynamic parts would be handling the parsed options and command arguments and either returning results or calling subcommands. This library was originally developed as part of Ubicloud, but earlier this year it was released as a separate library named Rodish. So in addition to being Roda-ish, the SH part of the name indicates it's related to the command line. So let's look at a Rodish hello world. Now Rodish is designed to be installed into an existing class, and instances of this class serve as the context for the argument parsing. Installing Rodish into a class requires calling rodish.processor with that class, and starting a new argument parse is done by calling the process class method with the array of arguments. And this creates a new instance of CLI example that will be used for the argument parsing. The class level on method sets up the root of the command parsing. So if you don't have separate commands or subcommands, you could use the root command to handle all command argument parsing. The block to on is executed in the context of the root command, and it's used for configuring the command. Now the run method sets the code to be executed when the command is run, and this block is executed in the context of the CLI example instance that was created in the CLI example.process call. So if you run this program with no arguments, it will print hello world. Let's add support for a command named hello. This will allow us to say hello to a specific person. This command will accept one argument instead of the default of 0 arguments. And the subcommand will have its own run block, which will be called when the subcommand is executed. We can run the program with hello and Jeremy as the arguments, and the root command will dispatch to the hello subcommand because the first argument is hello, and the remaining command line argument is Jeremy, which is yielded to the hello command's run block. So this will print hello Jeremy. And you can nest subcommands inside of commands with no limit on the depth of nesting. But this doesn't show the unique feature of Rodish, which is subcommands after command arguments. So let's change this to support an object-oriented style, where you pass the object to operate on, and then you pass the action to take on that object. And here's what that looks like. We start with loading the post commands plugin. Rodish, like Roda, Roda and Sequel, ships with many plugins. And not all programs need to use this object-oriented style, so it's included as a plugin that ships with Rodish instead of being part of the core Rodish functionality. The hello command now uses run on instead of on, and this will register it as a post subcommand and not a normal subcommand. And because post subcommands may support both options and arguments, when you're using post subcommands, you generally want to accept a range of arguments. And typically you would require at least two. The first to specify the object to operate on, and the second to specify the subcommand name. As you allow a range of arguments and not a fixed number of arguments, the arguments are yielded to the run block as an array. The options argument here would be the options hash parsed by the option parser. Now there are no options for this command, but in general, you pass the same options hash from the commands to the subcommands, and the option parsing supports disambiguating which command the options came from. And the final argument is the command object, which is used to dispatch to the subcommands. Now in this case, we take the first command line argument and we assign it to an instance variable, and then we dispatch to the post subcommands. And as the subcommand given was hello, this will dispatch to the hello post subcommand. And this run block is executed in the same context as the run block for the root subcommand. So we can use the instance variable already defined, and this will print hello Jeremy. The key advantage is really this line. Using this approach, you can share logic easily, so you don't need to repeat the logic in each subcommand. And this brings the primary benefit of Roda's routing tree to command line interfaces, or command line argument parsing. Now, I don't have time to do a deeper dive into Rodish in this presentation, but hopefully you can see that it is low ceremony and quite flexible. You may want to consider it if you're building a command line application. So using the Go-based command line program on the client and using Rodish to process command line arguments on the gateway endpoint, we added a command line interface to support our entire API command set. And while this made it possible to interact with Ubicloud from the command line, asking people to install a command line program without allowing them to test it out first is a bit of an ask. And I realized because there's almost no client-side logic, we could easily offer a web-based version of our CLI, so users could test the CLI just by logging into our web application. And this allows users to see how easy it is to use, so they'll be more inclined to spend the time to download it. So here's what Ubicloud's web shell looks like. You can input a command into the web shell, such as vmlist, to list virtual machines, and when you run it, you see the command that you ran and the output of the command. In this case, the vmlist display shows the location, name, ID, and IP addresses of the virtual machines. Most IDs in the command output are linked to the related page. So if you click on the link for this virtual machine, it takes you to the page to manage that virtual machine. Going back to the previous page, you may notice the multiple commands button. And this takes you to a page where you can input multiple commands. Let's say I want to create a firewall, and I want to create a private subnet using that firewall, and then I want to create a virtual machine inside that private subnet. If I click the run button, it will run the command to create the firewall, and I'll show you the output. It will also fill in the next command to execute and show you the remaining commands to be executed. If I click the run button on this screen, it will run the command to create the private subnet, show you the output. It will also fill in the next command to execute, which will create the virtual machine. This provides a simple way for users to walk through a multi-step setup process, and once users see how easy and powerful the web shell is, they're more inclined to spend the time to install the command line program so they can interact with Ubicloud from the command line. Now, one important thing to note here is because almost all logic is in the gateway endpoint, it took very little work to add this web shell. A working prototype of this web shell was written during a company hackathon in about an hour. I hope you had fun learning about the thin client approach. The key point to remember is that moving almost all the logic from the client to the gateway endpoint allows for the advantages of web deployment, and it simplifies maintenance. If you enjoyed this presentation and want to read more of my thoughts on Ruby programming, please consider picking up a copy of Polished Ruby Programming. I still have 3 free promotional copies left, so come see me if you want one. And that concludes my presentation.